Let's wait, maybe, yeah, okay, that's, I think it's time. Let's just get started. So the next presentation of mine is going to be an overview of real-time hybrid simulation technique. So in the morning I talked about some pseudodynamic hybrid simulation technique, and Jawad gave a very impressive presentation about all things they can do here, and he did before. So this one will be a little bit different. We haven't touched much about the real-time hybrid simulation. There are some special challenges when you move from slow to real-time hybrid simulation. So first, I'm going to go through very briefly about the solution, hardware and software. Again, Shawn Gao has already gone over that in the morning. And then into the technical part, I'm going to talk about the system dynamical stability analysis, because whenever you move from a quasi-static testing to a dynamic testing, the first thing you worry about is stability. When things start to move really fast, if you do not tune the system properly, you can go unstable. The real-time hybrid system has some other challenges. So in addition to the tuning. And then in order to tackle that challenge, we do need some other advanced control strategies in order to make the real-time hybrid simulation a reality. And then from the analysis model perspective, again, real-time hybrid simulation, you have to solve your model to keep up with the real-time constraint. And a lot of times, their FEA model, a lot of times is not fast enough. So we will talk about some reduced order model technique that can help you to tackle that challenge. So the motivation is already saw this page very briefly. When you are testing your testing article, not only depends on the stiffness, but also depends on the mass. It's significant mass here you cannot ignore. Or it's like this type of damping devices, then you have to do a testing in real time. That's the real dynamic testing. You cannot artificially slow down your testing anymore, right? Otherwise you don't get anything out of that. And our solution, again, we use a target PC, that's a real-time box. Whatever model you program, control algorithm you program, you can dump that into your real-time PC, and then this model can interact with our servo controller in real time through a ScramNet reflective memory. So, MATLAB and Simulink is, as far as I know, most widely used in the real-time hybrid simulation world, because it's easy to program. A lot of people know how to program Simulink and MATLAB. And servo controller, again, is on ScramNet. So the ScramNet communication is really fast. According to their technical specification, I think it's in the order of microseconds. So between two real-time boxes, you exchange information extremely fast. Nearly like those two systems are like one big real-time system. So that's why MTS chose the ScramNet solution to do that. And that's just a topological. And this slide shows you kind of like we talked about, like you could have a very complicated system, multiple seismic tables. Each has its own servo controller. You need to have some model in the loop. You have to have a target PC runs it. Then you could have a bunch of data acquisitions, everything linked through a ScramNet ring. So now on the ring, every machine is a node. Then they are all in real-time clock. So they all pass information. As long as the information shows up in one of them, then all the others are getting them simultaneously, nearly instantaneously. Okay, so now I'm going to talk a little bit about the dynamical stability analysis of a real-time hybrid system. So this is, we have to go through a little bit equations, but nothing beyond the structure dynamics. So I think that's the only way we can actually visualize that problem. So again, for any realistic control system, in the frequency domain, you see that the amplitude starts to roll off when you want to drive the system at higher and higher frequency, and you see this phase lag, right? That's just the nature of any control system, because you cannot drive anything instantaneously to whatever next set point you set. It has to take some time to reach there. And in the time domain, it's this phase lag, this delay. That's your command. Black line is your command, red is your feedback, meaning that you have some amplitude roll off, and also especially the phase. The phase delay is a big deal here in a real-time hybrid simulation because it causes a negative damping. So qualitatively talking, negative damping has been recognized by the community a long time ago. But what we want to show here is like quantitatively, how can we analyze this negative damping? So how does this negative damping associated with this time delay? So we want to set up an equation for that. That's the purpose for this slide. Basically, let's say we have a single degree freedom dynamic problem, right? Just MCK. And then we divide them up between the numerical portion and the experimental portion. That's the subscript N and E. Everything has to be divided, right? Mass, damping, stiffness, they can all be divided into numerical and the experimental part. So then what we want to do is we want to come up with a hybrid system equation motion. So what happens is when you have a hybrid system, again, due to the control system error, your experimental substructure, the state is different with the numerical one, right? The numerical one is the ideal state, displacement, velocity, acceleration, but the experimental part has some error in there. And this error, we can simplify it by just use an amplitude term and the phase term. This is a phase error, this is the amplitude error. So it's actually, has a phase delay and also amplitude error. So then we do some simple linear approximation. We can write out these quantities as a function of the ideal state, right? Now everything is expressed as x and the derivatives of x. So then you plug this thing back into your equation of motion, then you come up with the equation of motion for a hybrid system. So now you see for the original reference system, it's just a single degree freedom oscillator. But when you divide them up, and then now become a little bit more complicated equation of motion. And especially what's interesting here is that you see, because this associated with the velocity term, that's the damping term, right? That's the damping term for the hybrid system. And you see there is a negative sign here. That means your experimental substructure stiffness contribute to the negative damping of your whole hybrid system. And if you have a very steep structure you are testing there, it doesn't take much of a control error here. This system will be going to a negative damping part. Then the system will go unstable immediately. Before you just start your code, just start then the blow up. The test will blow up. So that's the nature of this negative damping thing. But another thing we want to point out is this negative damping actually depends on two different aspects. The blue one aspect is the actuator control error. Say that I have a phase error, I have a amplitude error. I can try to do a good compensator to reduce that error. But on the other hand, it also depends on this green part, which is like this depends actually only on how do you divide the substructure. That when you are planning a real-time hybrid simulation, how much damping, how much stiffness, how much mass am I going to put in the physical part? That actually just depends on the substructure partition. So basically, if you really look at this equation a little bit more, you can come up with some different cases. For example, you can come up with some case that this term can go to 0, right? If this goes to 0, then you could have a lot of experimental error, control error. Your system will still be there is no negative damping because they cancel out. This term can be there. So that's the case you don't care too much about the actuator control error. But in some other cases, it's like you have to be careful, very careful. For example, in this case, you have the physical specimen all being pushed physically, like the whole frame specimen is physically tested, and then you have a numerical mass assumed. A lot of testing in the pseudodynamic hybrid simulation world started with this type of thing, right? Because the advantage is that I don't have to assume add a big seismic mass on my physical structure. Instead, I can model it. In the pseudodynamic world, it doesn't really, it's not a big deal. You can slow down your test, and then this negative damping doesn't show effect. But when you go to the real-time world, this guy is going to give you so much negative damping. What I'm plotting here is a curve that shows, for example, for this single degree freedom oscillator, this is the frequency, natural frequency of this guy. So the natural frequency, if it's 1 Hertz, then about 6.5 milliseconds of a delay could cause this system go unstable. But as you go up and up, this guy, if the natural frequency is high, let's say go up to 10 Hertz, then less than 1 millisecond of delay will blow up your system. That means you need to get a really good control. Your physical substructure, your actuator control has to be extremely precise. This is only the stability. Imagine that if you want to come up with some meaningful testing results, like a performance, accuracy, then you have to way below 1 millisecond. That's like you are beating the controller clock rate. You almost have to achieve a perfect control in order to do this type of real-time hybrid simulation, right? So then we go to multiple degree freedom because we started that is a single degree freedom. Go to multiple degree freedom, everything becomes matrix form. But the same thing, you can solve this thing using the model coordinate system, and that's just the structure dynamics, right? You convert from the natural coordinate system X into the model coordinate system. And then again, we do the same technique. We assume each mode, because in the model coordinate system, you are talking about each single mode, mode 1, 2, 3, until mode n. Every single mode, you could have different delay in there. And once you plug this big equation, linearize it first, and then plug it back into the original equation motion, and then that's become your hybrid system equation motion. So now it's actually becoming a little bit complicated. A lot of matrix in here, and a lot of things like the mass, the damping, and the stiffness, they all contribute to your real-time hybrid system damping. But again, this is the most dangerous part because it's negative sign. That's the negative damping. So why we are constructing this equation motion? Because that's like, you have the equation motion, you can study the system. You can do frequency domain study, you can do time domain, time history analysis, whatever you want to do to analyze this hybrid system. So that's, using this demo example. So it's a steel structure, grids in both directions, 1.5 meter tall each floor. So this is actually a physical system. It's actually a real structure being tested in one of our clients in China. So in the beginning, what they want to do is they want to test this. They did a shake table testing, then they want to do the real-time hybrid simulation to compare the results. So then naturally we say, okay, you already have the physical frame all constructed. Let's just do this real-time hybrid, right? You have those maps, you can assume them in the numerical part. But remember, that becomes like a very bad choice for substructure. So what happened is that, for example, that's like the frequency response function or the transfer function of your hybrid system. This is the reference system before you divide the system. It's like the whole structure. The 3 mode, right? These modes are quite high. 7 Hertz, the third mode is like 34 Hertz. Quite steep structure. That because of braces, the steel braces make it very steep. And then if you look at the poles of the system, again, the 3 modes, first mode, second mode, and third mode. So these are all good. of course, your structure itself is a stable system, but when you do the hybrid, again, using this type of divided substructure and using the equation of motion we just derived, and if you look at your hybrid system frequency response function, that's the red one. Here I'm assuming just 1 millisecond of delay at all three modes, and you see that the second and the third modes, they are actually unstable because they move to the right half of the plane, meaning that your response will grow exponentially with respect to time. If it's on the left, then it's actually decay, right? That's the damping effect. Positive damping, your system response will decay, but negative damping is like you blow up. Let's just give you an example. Using that equation, we can actually do a pre-assessment like screening. Say, okay, that plan is probably not going to work. It's too critical about the control. 1 millisecond, all three actuators, all the cross coupling, it's probably, I don't think it's going to happen. So, then we said, okay, can you design a different case? Usually it's like, what if I just assume a lot of mass in the system? It's like just arbitrary. And then the mode, of course, goes down once you have a lot of mass in your system. And then, let's then take a look. I started to look at my hybrid system, 1 millisecond of delay, everything stable. Of course, you see some negative damping, it's shifting to the red half plane, right? And 3 milliseconds, it shifted more, but still they are stable. You see those are very high peak. 3 milliseconds is still okay. 4 milliseconds, actually, your system is unstable now. You can also see it from here, unstable system. So we did some analysis, and we want to validate if those equations actually make sense, right? Then we did a virtual real-time hybrid testing. So in a way that we assume, the same FEA model OpenSys being constructed, and target piece, everything, but only is that instead of driving the physical rig directly, we build a model in Simulink to simulate this specimen, and then see how this virtual real-time hybrid system works. So we did, this is like the reference solution without substructuring, without hybrid simulation. And then we said, okay, let's introduce 1 millisecond of delay. Okay, I forgot, I should mention this is design case B. We analyzed, remember, 1 millisecond is okay. Now stable, 3 milliseconds start to show this kind of local instability. We actually predicted that, remember, using the equation of motion. We said 3 milliseconds was about the borderline. And if you go 4 milliseconds, of course, I cannot show it here, it's just blow up. So this is just a kind of virtual testing validation about the equation of motion we constructed. And another demo example here I want to show here is just a very different substructure now. It's like Javad shows, like if you have a lot of numerical elements, like all these other elements are modeled numerically, and what if we are only testing one of the column specimen? So that's a different substructuring, completely different hybrid configuration. But this case, actually, that's the modes. And we start to introduce delay. 1 millisecond is nearly, very good. It's pretty close to the reference system. 10 milliseconds, you can see some negative damping effect, but overall, it's very stable system. Goes up to even 35 milliseconds, that's where the second mode started to become a little bit unstable. You can see here too. So 30-something milliseconds, so that should be a pretty easy real-time hybrid simulation. You can comfortably conduct, right? And again, using that virtual hybrid simulation validation, that's the reference response. At 1 millisecond of delay, same thing. So practically engineering talking, it's the same response. So 10 milliseconds, you see those negative damping things. And then, go up to 35, then of course the system response becomes, it's not accurate anymore. This result probably it's not acceptable, but at least it's still stable. So that's about that. That's just when you are dealing with a real-time hybrid system, be really careful about the system delay. 1 millisecond could actually make your system just go below for a while. And then how can we tackle that problem? We have to use some advanced control strategy to reduce the actuator control error to make it to be within 1 millisecond. And we have some good algorithm we can, at least on some testing, we can make it pretty good. So that's one of the adaptive feed-forward compensation. Shawn Gao actually mentioned it in the morning too. So look at your system plan. It's like your actuator, your specimen, everything. This is adaptive inverse compensator. So basically, it's going to try to invert your system, and then so that you cancel out all the dynamics. And the good thing is that these parameters are all adaptively changed online, right? So that your system could be a nonlinear, then those parameters will actually follow that to make sure the control accuracy is still maintained. So I don't want to go much detail. I think this is too involved, and this algorithm was first proposed by Professor Che in Lehigh University, and then he shared with the MTS. The MTS did some improvement to make it solving much faster. That's another thing, right? You have to solve these controllers become very mathematically involved. You have to improve the execution speed of that too. So this one in Tongji also Shawn Gao already mentioned. So actually, using that AFC compensator make sure this testing can be done successfully. And another type of compensator is like a H-infinity loop shaping control. The adaptive control was one strategy. This is a different strategy. This is a closed loop control system. Assuming this is your actuator dynamics and this is your controller. So what we do is we shape the open loop gain so that we can make this feedback follow the desired signal. So, I don't want to go in much detail. If you anybody interested, I think we can talk offline. But the idea is that I shape the open loop gain so that my closed loop specification can be met. If the open loop gain is very high, then the transfer function here is that this T0 becomes 0, then you can achieve a very good tracking. But when you have a very high open loop gain, the system tends to be very, cannot tolerate much of the system uncertainty, nonlinearity or anything, small disturbance. If you have a very, very aggressive controller, your system tends to go unstable very quickly, right? Because ideal world, you design everything based on a model, but when you do the real testing, the model cannot 100% represent your real hardware, right? So that's the thing, the trade-off you have to achieve. So it's a modern type of controller, so we did some validation, the two different actuators attached to a two-story frame. And then what happened is look at the frequency response function matrix. Before we attach the outer loop H-infinity controller, so this is like the coupling, right? Ideally, we should get a 1 at the diagonal term, meaning pushing this one will just move the same as the command. But the thing is that it's not 1 because you have the coupling. The second one is actually going to couple with the bottom floor. And then the off-diagonal term is actually the coupling, really, the coupling, like 20–30% of coupling. You push one of them, the other gets retracted, and push the other one, the first one gets retracted. And then using the H-infinity loop shaping, so it actually can make this coupling minimize those couplings. And then this one is also closer to 1, right? The diagonal term also close to 1. Another important thing is that this is the delay. Remember how much delay we had before we plug into this outer loop H-infinity controller. Once we do this, bring this controller in, the delay nearly goes to 0. And that's the thing. We don't want any delay. We want 0 delay, if possible. So then we did a real-time hybrid testing using that one and the two-floor response. and that's zoomed in, you can see they are very accurate, meaning that our controller works pretty good. And the frequency response function-wise, this is pretty good until. But then when you have output controller, you're introducing some artificial mode. I think some of the speakers before was also talking about that. But this mode is actually far off from our main mode, the first and second mode. So in the time domain, you don't see much participation of that artificial mode. So that's the test. And last bullet point is the reduced order model. I will be quick. So in many cases, like the FEA model is just too complicated, and you cannot run it, you can never run it in real time. So how can we do that? But if we still need to test something, in real time, well, one thing we can do is we can construct a reduced order model for that. So what does it do is that you have a FEA model, you do a model analysis, and you get all the interested mode. Maybe the first 4 or 5 modes or whatever number of modes you want. Then this thing can be converted from a FEA into a transfer function matrix. Because you are only interested in the global dynamic mode, I'm not going to care about the stress and strain, those things. So we can convert from FEA model to a simple, simple transfer function matrix. This again the same setup I showed you in the morning. We did a pseudo-dynamic hybrid simulation, and but when we do real time, we cannot do a FEA anymore. But we can convert this model into a simple block in Simulink. That's a reduced order model. Once we convert that, then we can do easily a real-time testing, because that reduced order model is very efficient to solve. It doesn't take much CPU time at all. So that's actually a hard real-time hybrid simulation. So that's just one of the ways that you can do a real-time hybrid simulation. If your numerical substructure is fairly linear, you can use the reduced order model technique to do that.
So at that top right block, was that a Simulink block within obviously or something?
This one?
On the screen there, when you ran the video,
Uh-huh.
right-hand corner, was that a Simulink block?
Okay. So yes, this is a Simulink block. But then we convert this model again onto the real-time target PC, and all those code are actually being executed on a real-time PC. So that's this PC. This is the real-time PC actually running the model, everything. Yeah. So in summary, we need to be very careful about a real-time dynamic system, hybrid system. You need to do a lot of things. You can do some pre-screening stability analysis to know if your design is good. If you are, your substructure selection is possible to do the hybrid simulation. And then this negative damping, again, depends on the actuator control error, but also depends on how you define your hybrid system. And we use virtual testing procedure to help before do any physical testing, really to know that, to gain confidence. And then we have advanced control strategy to perform real-time hybrid simulation, reduce that delay as much as we can. And the reduced order model is just an effective way to convert your full-blown model into a reduced, easy model to be executed in real time. So that's it for my presentation today.
So Shawn, when you use the reduced order model, what do you give up? You give up the ability to know what the strains really are, and you get accurate deflections, or what is the trade-off?
Yeah, the trade-off is all the stress and strain information, they are all missing. But you can maximally preserve all the global dynamics, meaning that if you look at the displacement, velocity, acceleration, they should be very close to the full model. Yeah.
this reduced order based on which method? The conventional method of model reduction or?
The reduced order model? It's actually just based on model analysis. Like you do a FEA, in any FEA you can do a model analysis, right? Then you use the eigenvalue and eigenvector, you can reconstruct that reduced order model.